been a little bit since I made a video. I thought it's about time. Baz, I'm sorry for your kitty passing away. I've also had a kitty pass away. I think Onyx was my all black cat. I think she was attacked by a dog. I found her and she wasn't in very good condition, so my heart goes out to you, man. Sorry about your kitty. Um, and at work I've been working overtime a lot. I've been really tired. But I think I'm gonna get back into the groove, trying to get things sorted out. I'm taking chemistry right now in college, and we're reviewing exothermic, endothermic, and thermochemistry. So this is kind of gonna be like a new thing for some people, but this is where my mind is headed. I put this paper on Vixra, but Vixra was giving me some problems, so I put it on my blog, and I'll link that to the bottom, and then I'll link the Vixra paper. But this is the iron nickel cores of ancient stars as leftover catalyst. I'll read this out to you guys. It is explained that the iron nickel cores of ancient stars are composed of unconsumed catalyst used in the chemical reactions required to form many chemical compounds found on rocky, highly evolved stars. It also explains why only specific elements are found with the iron nickel composites in a larger amount, given they're also trace amounts. It is because they also function as catalysts, such as platinum, copper, and gallium, which can be unconsumed in the process. Now, basically what happens here is as the star cools and collapses, iron from the environment enters into the star and acts as a catalyst, meaning it lowers the activation energy for a lot of the chemical reactions to take place. So you have a certain amount of energy a reaction needs to happen, and if you have a catalyst there, the catalyst makes the energy lower so the reaction will go by easier. And catalysts such as platinum are used in catalytic converters inside of cars, which clean up the exhaust. As well, you use catalysts in what's called the Haber process. Now, the Haber process is pretty straightforward. It combines nitrogen from the air with hydrogen, derived mainly from natural gas, which is methane, into ammonia. The reaction is reversible, and the production of ammonia is exothermic, meaning it releases heat. So you have 1 mole of nitrogen gas, which is N2, and that's what that G means right there. And then you have plus 3 moles of H2. That's also a gas. That's hydrogen. Duh, hydrogen. Now a mole is like a number. MOL. It means it's 6.022 times 10 to the 23 parts of something. A mole is like a billion or a trillion. It's just a specific count. And they have it set to, I believe, carbon 12. So 1 mole of carbon 12, which is 1 carbon atom, carbon 12, 6.022 times 10 to the 23 carbon atoms weighs 1 gram. I believe that's it. So if you have a mole of hydrogen gas, it's going to be less than a gram because hydrogen is less weight than carbon. I think it's 1/12 the mass of carbon, because it has less nucleons inside the nucleus. Now, basically what happens here is you combine the nitrogen and hydrogen, and you get NH3, which is ammonia. Yeah, ammonia. And then the change, that little delta right there, that little triangle thing, the change in heat is negative 92 kilojoules a mole. What that means, that negative 92 means it's exothermic. If it was positive, it would be endothermic, meaning heat absorbing. Another exothermic reaction would be rocket fuel. Rocket fuel, when you take liquid hydrogen and liquid oxygen and you combine it together to make water, That's what the Space Shuttle RS-25 engines used when the Space Shuttle went up. Very, very powerful exothermic reaction. And the reason why I'm going over this is you have iron as a catalyst. Iron makes a really good catalyst, believe it or not, when it comes to high temperature and high pressure reactions. So basically you have nitrogen from the air, hydrogen from natural gas, and then you have 1 to 3 by volume nitrogen, hydrogen, and you have unreacted gases recycled, but then you have 400 to 450 Celsius, 200 atmosphere iron catalyst there, which is oversimplification, because it says here the catalyst is actually slightly more complicated than pure iron. It has potassium hydroxide added to it as a promoter, a substance that increases its efficiency. And then it says here the pressure varies from plant to plant, but from manufacturing plant to manufacturing plant, but it's always high. And it says here you can't go far wrong in an exam quoting 200 atmospheres. So when you have the iron entering into the star to act as a catalyst, combining, which then can combine the hydrogen with the nitrogen, making ammonia, it can be very high temperature and very high pressure naturally, because that's what meteors do naturally. When they enter into the atmosphere of a star, they heat up really hot, and it causes all the surrounding material to react on the surfaces of the meteor, and it can make a whole bunch of random chemical compounds. And what happens is, over time, if you have enough of this iron entering into a star where all the hydrogen and where all the nitrogen is, you're going to make a hell of a lot of ammonia. And that's exactly what happens. But since the iron acts as a catalyst, and a lot of the times it goes unconsumed, meaning it doesn't combine with any other elements, making heavier and heavier iron compounds like magnetite or hematite, it will then sink into the center of the star in a purified form because it's not consumed. And that purified iron and nickel, which were the catalysts from the beginning when it was making a whole shitload of ammonia, will sink into the center of the star. And what that means is that we can figure out how much chemistry occurred inside the star as it evolved to its basically dead state, how much chemistry actually occurred by measuring the diameter of the inner iron nickel core. And for instance, here's a good representation. If you have very, very, very low amounts of catalytic material that had collected in the center of the star, you're naturally going to have a very small object because the star only had so much material to work with. If it couldn't combine the material, the elemental materials together, then there would be less material to form rocks and minerals out of. Thus, the star in its dead state will be a lot smaller. The objects that have much larger cores, you have a lot of catalysts enter into the star. It can make a lot more chemical compounds because there's a lot more catalyst available. See, so small amounts of catalyst, small end remaining dead star. Lots of catalyst, huge amounts of chemistry having occurred, huge oceans, huge everything. It's just really, it's a really big deal, like the Earth. I consider the Earth to be a big deal, you know. I don't know, Carl Sagan, if he was still alive, to him it's just a tiny little thing. But to me, the Earth is a big deal, and I'm sure it's a big deal to you guys too. There's low catalyst, which would make intermediate objects, and then you have medium catalysts. But basically, you have lots of chemistry happening inside the star as it evolves. And astronomers, they somehow forget that chemistry is essential science. Now, do this for me. Go to Wikipedia and go to the Nebula Hypothesis page. Find all the chemistry in there on that page where they explain how a planet forms. Find all the equations where it shows, like this. When these two arrows are, forgot to tell you, these two arrows right here means it's a reversible reaction, so it can go either direction. Now, if it's, going this way, it would be obviously exothermic, but if it goes this way, chances are it's endothermic. And a good rule of thumb is, I don't think this is always true, but a good rule of thumb is to make more and more complex molecules where more atoms are combined together. That's going to release heat, and that's exothermic. To make more and more complex, bigger molecules, those are for the most part exothermic reactions, because you're making bonds. You have to get rid of that extra energy to make those bonds. And for endothermic reactions, for the most part, you're absorbing energy, and you break the bonds with those. So endothermic reactions would make bonds even smaller. So anyways, go to the Nebula Hypothesis page and look at all the non-existent chemistry that they use to explain how planets are supposed to form. The most complex process in the entire universe, physical process in the entire universe, the very process that makes life itself, they just completely ignore chemistry. And chemistry is essential science. It feels as if they live in this quasi bubble of, I don't know, like a fantasy, if you will, and they have actual chemistry available to them, but they don't even mention it. It's like they're afraid of it. Anyways, I'll make some more videos. I just want to let Baz know and some others know that I'm feeling a little better now, and I'm gonna start making more videos again. And things are gonna change, man. I'm telling you. Later.